What is time? We all think we understand it very well until someone suggests that we try to define it. That's when most of us realize we don't know what words to use to describe time. Worse still, the more we think about time, the more complex the topic becomes, and it tends to inadvertently evoke mystical elements that are often prevalent in science fiction works. Have you ever wondered about the essence of time? Science suggests that it is a linear dimension, while some perspectives argue that time moves in cycles or circles, like the seasons in a year. Although many people in today's era seem to agree that time is linear, when we look at the historical existence of humanity, we see that time has a cyclical nature and changes in rhythm. Ultimately, what is the nature of time, and does it truly exist? This is the issue that we will explore and answer together in the upcoming video, Illusion of Time. Einstein once said in the theory of relativity decades ago, "There is no unique and absolute time. The time that humans conceive of is only an illusion." In January 1989, to demonstrate this theory, NASA conducted an experiment called the Time Evidence. The experiment involved digging a cave several tens of square meters wide at a depth of 150 meters underground, adjusting the temperature, humidity, air, and living conditions inside to be identical to those on the surface. NASA adorned the room with utmost comfort and luxury, providing all necessary supplies, food, drinks, beds, wardrobes, tables, chairs, and household items. After a period of candidate screening, Foligny, a 27-year-old girl from Italy, was selected for the experiment. The notable difference in the cave was the absence of natural scenery outside, no changes, and no time-marking objects. Time on TV and computers was completely erased. From the moment she entered the cave, the participant would live in the dark basement, without the need for work except eating and sleeping. She could freely entertain and relax as she pleased. This lifestyle appealed to many, attracting numerous volunteers who registered due to the attractive rewards offered by NASA. Foligny, the participant in the experiment, is a designer who constantly faces a busy and exhausting life due to her job. She volunteered for the experiment seeking a life without stress, with abundant food and drinks, and without the need to continue working. The controlled environment intrigued her, and Foligny, with good physical health and well-rounded mental qualities, was excited to have surpassed 10,000 candidates to be part of this project. When asked how long she could stay in the cave, Foligny confidently stated, "If given enough food, drink, clothing, and entertainment, I could stay there for a lifetime." From the monitoring screen, one could see Foligny's cheerful smile upon observing the luxurious decoration in the underground room. The laboratory space was not large, only 18 square meters, but it was sufficient for Foligny to live comfortably. NASA also announced that if she wanted to stop midway, she could press the doorbell to return to the surface earlier than planned. Initially, Foligny seemed quite comfortable, eating alone, playing games, watching movies, and resting when tired. However, in less than 2 weeks, she started feeling bored. Foligny decided to enrich herself by using this free time to acquire knowledge. However, because the room lacked a time display, her previous life routines were almost turned upside down. Foligny needed to learn when to rest, when to eat, when to read, and when to sleep. She could only follow her instincts and what her body sensed, with the brain in control. After a while, scientists observed that Foligny would only sleep for 1 hour, wake up to eat, and read, sometimes sleeping for 2 days before waking up again. Her health deteriorated, often muttered to herself in a semi-conscious state, losing interest in her favorite foods or movies. Concerned for her health and safety, scientists decided to halt the experiment before things worsened. When brought back to the surface, due to being alone for an extended period, she struggled to adapt to the sunlight, experiencing stiffness in her body. Doctors reported both her physical and mental health were severely compromised. Once Foligny recovered, scientists asked her how long she thought she had been in the cave, and she believed it was 60 days. However, in reality, she had been there for 130 days. This serves as evidence that in a state of timelessness, humans find it challenging to regulate themselves. In reality, we can always rely on clocks to organize our schedules because time is a unit established by humans to regulate their behavior. Without this structure, living organisms can fall into a state of chaos, leading to danger or even extinction. For humans, time has become an indispensable part of life. However, from a broader perspective, the time of the universe does not reveal such characteristics. Linear time. Science always strives to uncover the true nature of grand and abstract concepts, such as time. With the current scientific understanding, most people agree that time is likely a linear dimension. Why is that? Several reasons are put forth to explain this viewpoint. Firstly, time is irreversible. Reality demonstrates that we should not believe in movies like Back to the Future, The Flash, or the science fiction novels of H.G. Wells. Time travel backward is simply implausible. As living entities, we are born, grow, and eventually perish, following that chronological order. We know about the past but cannot know the future. This is because time only moves in one direction, not in terms of perception, but as a reality according to natural science. Additionally, the second law of thermodynamics indicates that time is linear and unidirectional, as everything in our universe tends to move from an ordered state to an increasingly disordered state. A hot cup of tea will cool down rather than heat up. A dead body will decay instead of regenerating. A car will deteriorate, and humans will age. You may deny that these things are, and will happen, but someday you won't be around to deny them anymore. Ultimately, time is considered linear because we have various ways to record and measure it, and the recording and measuring can occur cumulatively. The stopwatch on our smartphones, for example, can measure time down to milliseconds. However, it would be absurd to measure everyday activities with such precision, unless an athlete wants to track and push their speed limits. We can also measure time by counting the number of Earth's rotations around the Sun, as humans have been doing for thousands of years. If counted in this way, time appears as a linear process starting from a point and extending forward. Alternatively, we can measure time by observing the vibrations of cesium-133 atoms. This is how scientists establish the International Atomic Time, IAT. This global standard is so accurate that it would take 1.4 million years for it to deviate by just 1 second. These natural phenomena can be recorded in long, cumulative, and linear sequences. Cycle time. Nevertheless, there are also ideas suggesting that time has cyclical and repetitive aspects. Firstly, many commonly used time measurement systems in our daily lives are cyclical. 60 seconds make a minute. 60 minutes make an hour. 24 hours make a day. 7 days make a week. 4 weeks make a month. 3 months make a season. And 4 seasons make a year. So, isn't the sense of déjà vu that we often experience, and the repeating patterns in history, evidence that time has a cyclical nature? If time truly has a linear essence, why don't we use linear methods of measuring parameters, starting from a single point and extending forward to infinity, like measuring distances? Furthermore, humans don't necessarily need linear, orderly methods to measure time. Even today, the lives of farmers, nomads, and urban dwellers are governed by an endless, repeating seasonal cycle. Calendar systems, originally designed to express time linearly, are a relatively recent phenomenon when compared to the long existence of our species. The earliest calendars date back to 10,000 years ago, and carefully recorded calendar systems have only become widespread in the last 5,000 years. Considering that our species is 200,000 years old, meaning for at least 95% of the time humans have existed, time was something cyclical and measured by days alone. In the end, calendars are cultural and artificial constructs. Have you ever noticed that the year in the calendar, or the linear time frame, is counted as accumulated units from a specific starting point? This is because the calendar year is used by political and religious authorities to mark events they consider important, such as the birth of Jesus, rather than natural or scientific events or processes, such as the origin of life on Earth. What are the differences between the Jewish, Chinese, Gregorian, Christian calendar, Western calendar, or solar calendar, and Mayan calendars? Not many, considering the concepts and perspectives of time. These calendars have different origins, starting points, counting systems, and various holidays, and they are only relevant to humans, not to animals, plants, or planets. Ultimately, each calendar is nothing more than a cultural construct built upon the political, religious, scientific, and economic systems of a region, all created by humans. Human beings have a complex relationship with time. Our modern lives are almost comically structured around linear time and precise time measurements. However, our human ancestors and some of our relatives today lived with a different understanding of time, a cyclical, daily, and rhythmic understanding. This is also why time becomes the most mysterious existence. It exists, yet simultaneously does not exist. Simply by changing our perspective and reconsidering the definitions created by humans, one can discover that time does not truly exist. Before humans had intelligence, the universe was there as it always had been, independent of humanity's definitions. This is the greatest deception that not everyone understands and recognizes. Space-time. In 1915, Albert Einstein published the general theory of relativity, describing gravity as an inherent property of space-time. He presented a set of equations describing the deformation of space-time about energy and momentum. According to Einstein, gravity is not just an ordinary force, as discovered by the physicist Isaac Newton. Gravity can be considered as the curvature of space-time caused by the mass of objects. He demonstrated that time is created by matter. Time does not exist independently of the universe and comes into existence after the Big Bang. Einstein's theory also explains the characteristics of black holes, where gravity is so strong that even light cannot escape. According to the theory of relativity, gravity also distorts time, whereas in regions of strong gravity, time passes more slowly. Einstein also proved that in the entire universe, time is something relative. It passes more slowly for those on a spaceship moving near a massive black hole or traveling at speeds close to the speed of light. In the 1970s, physicists Stephen Hawking and Jacob Bekenstein noted the relationship between the surface area of black holes and their microscopic quantum structure. This marked the first insights into the connection between Einstein's broad theory of relativity and quantum mechanics. In less than 3 decades after that, theoretical physicist Juan Maldacena observed another connection between gravity and the quantum world. This connection led to the creation of a model with the idea that space-time can be created or destroyed by changing the entanglement between different surface regions of an object. In other words, this implies that space-time is a product of entanglement between objects. To explore this further, researchers Chun-Jun Cao and Sean Carroll from the California Institute of Technology conducted a series of experiments. They wanted to see if they could obtain the characteristics of gravitational force, as known in the broad theory of relativity, by using a framework where space-time arises outside quantum entanglement or not. By employing an abstract mathematical concept called Hilbert space, Cao and Carroll found a similarity between the equations governing quantum entanglement and the equations of Einstein's theory of general relativity. This supports the idea that space-time and gravity emerge from entanglement. Today, most of what we know about the physical aspects of the universe can be explained by either the theory of general relativity or quantum mechanics. General relativity has proven its role perfectly in explaining the behavior of objects on very large scales, such as planets or galaxies. Meanwhile, quantum mechanics helps us understand things on a very small scale, such as atoms and atomic molecules. However, these two theories seem incompatible with each other. This has led physicists to seek a grand unified theory, a single framework that can explain everything, including the nature of space and time, because gravity and space-time are crucial components of everything. Carroll believes that the research he and Kaku conducted can promote the pursuit of a coherent theory between general relativity and quantum mechanics. However, he notes that this is a challenging task. Nevertheless, if we can find such a theory, we may answer some of the biggest questions that scientists are currently facing. In the future, we will strive to understand the true nature of dark matter, dark energy, black holes, and other mysterious objects in the universe. Before the Big Bang, time did not exist. 2 weeks before his passing, physicist Stephen Hawking managed to submit his final research on parallel universes. Alongside co-author Thomas Hertog, he also made predictions about the end of the current universe. Their research, titled A Smooth Exit from Eternal Inflation, was published in the Journal of High Energy Physics. According to Hertog, Hawking completed the research while in his sickbed, leaving behind a legacy worthy of a Nobel Prize. However, Hertog's wish would never come true, as the Nobel is not awarded posthumously. The research by the two scientists is based on the string theory and the no-boundary proposal introduced by Stephen Hawking and American physicist James Hartley in 1993. This theory suggests that before the Big Bang, time did not exist. After the significant explosion, the early universe would undergo exponential expansion, known as inflation. This theory leads to the consequence that many different regions continue to expand and never reach the endpoint of inflation. This results in a state of eternal inflation, where new universes continuously emerge within other universes, creating an infinite number of universes. According to this theory, our universe is just a part of a multiverse with inflationary processes concluding, while new universes continue to develop continuously in other regions. However, this model cannot be tested because an infinite number of universes cannot be measured. Hertog mentioned that Hawking was dissatisfied with this limitation and told him, "Try to tame the multiverse." Therefore, the duo attempted to turn the concept of the multiverse into a testable model. In their new research, Hawking and Hertog used a technique called three-dimensional picture, reducing the three-dimensional space to 2 dimensions, making the calculations more manageable. From there, they observed the potential existence of a finite number of parallel universes instead of an infinite number. Following Hawking's reasoning, the multiverse would leave an imprint on the cosmic microwave background radiation passing through our universe. With a spacecraft equipped with suitable sensors, scientists could measure the background radiation and verify the existence of parallel universes. Many scientists view Hawking's work as a groundbreaking step in the field of cosmology. However, turning the idea of testing the multiverse by measuring background radiation into reality remains a significant question. Thomas Hertog himself acknowledges that current technology is not sensitive enough for such measurements. On the contrary, this theory faces criticism, with many scientists suggesting that Hawking and Hertog's arguments rely on unverified and incomplete theories. They believe that the duo is working with a toy model that is not fully developed and rigorous. Even they admit that there is much work to be done. Arguably, the most controversial aspect of Hawking's work is his prediction about how our universe will end. He posited that our universe will ultimately fade into darkness as stars run out of energy, leading to humanity's demise. The renowned physicist often made predictions about Earth's future as well. In June 2017, at the Starmus Festival, an international gathering that honors astronomy, space exploration, music, art, and allied sciences such as biology and chemistry, Hawking stated that humans should find ways to move away from this planet before it's too late. He believed that Earth would eventually become unsuitable for life due to climate change, pandemics, and overpopulation. The new generation should seek alternative habitats in space. We are running out of space, and the only places we can go to are other solar systems. It is time to explore other solar systems. Spreading out may be the only thing that saves us from ourselves. Parallel universe. Perhaps you've heard of the thought experiment involving Schrödinger's cat, a cat confined in a sealed box. Opening the box allows us to observe one of the possible outcomes in the cat's future, including the scenario where it is both alive and dead. This may sound illogical, simply because human intuition is not accustomed to such an idea. However, it is entirely plausible, based on the peculiar principles of quantum mechanics. The reason this can happen is that the potential spaces in quantum mechanics are quite extensive. Mathematically, a quantum mechanical state is the sum or superposition of all possible states. In the case of Schrödinger's cat, the cat is a superposition of two states, alive and dead. Let's interpret this more straightforwardly. Think of all these possibilities as pages in a notebook, where we can only observe the correct objective state of the cat. However, we can also choose to accept all these possibilities, suggesting that they exist in different universes within a multiverse. The cat might still be alive in this universe, but dead in another, though we can only observe one state here. The string theory is one of the most promising avenues for the potential unification of quantum mechanics and gravity. It is the only theory that can simultaneously describe all known forces in nature, including gravitational, electromagnetic, and nuclear forces. However, for the string theory to operate mathematically, it requires at least 10 physical dimensions. Therefore, any additional dimensions in the string theory must be somehow hidden, if they truly exist. To use the string theory to explain the physical phenomena we observe, these additional dimensions need to be compactified by rolling them up into sizes so small that they cannot be observed. Another characteristic of string theory is that there are many ways to compactify, 10,500 ways. Each of these compactifications would result in a universe with different physical principles, such as different masses for electrons and different gravitational constants. However, the question arises, in which of these possibilities are we living? String theory itself does not provide a mechanism to predict this, making it impractical as it cannot be tested. Fortunately, an idea in the field of early universe cosmology has turned this technical difficulty into a distinctive feature. In the early stages of the universe, before the occurrence of the Big Bang, the universe underwent a rapid expansion known as the inflationary epoch. The initial inflationary period was proposed to explain why the observable universe appears nearly uniform in temperature. However, this theory also predicts a range of temperature fluctuations around the thermal equilibrium. This has been confirmed by various spacecraft such as the Cosmic Background Explorer, COBE, satellite, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck Space Observatory. While there is ongoing debate about the specific details of this hypothesis, physicists widely acknowledge the concept of the inflationary epoch. However, an inevitable consequence of this hypothesis is the existence of other regions of the universe still undergoing accelerated expansion. Due to the quantum fluctuations of space-time, some parts of the universe have never truly reached the final stage of the expansion process. This implies that the universe, at least according to our current understanding, will continue to expand indefinitely. Some regions of the universe may therefore become distinct universes, which, in turn, can become other universes. This mechanism leads to the creation of an infinite number of universes. By combining this scenario with string theory, it is possible that each universe would exist with a particular compactification of additional dimensions, resulting in distinct physical principles. The universes predicted by string theory and the inflationary hypothesis would coexist in the same physical space. They might overlap or collide with each other. Indeed, they are likely to collide, leaving traces on the cosmic sky that we could potentially search for. The specific details of these traces depend intimately on the models of the universes, ranging from hot or cold spots in the cosmic microwave background radiation to anomalous voids in the distribution of galaxies. However, since collisions with other universes must occur in a specific direction, any such traces would likely break the apparent homogeneity of our observable universe, which is a common expectation. These traces are actively being sought by scientists. Some are searching for them directly through evidence in the cosmic microwave background radiation, which is the residual glow after the Big Bang. However, no such traces have been discovered yet. Others are looking for indirect support, such as gravitational waves, which are ripples in spacetime generated by massive celestial objects moving. Waves of this nature could directly prove the existence of the inflationary phase, thereby supporting the hypothesis of multiple universes. Whether we can prove their existence in the future remains uncertain. Nevertheless, given the profound implications, the effort to search for these traces is entirely worthwhile.